Hello everybody. In this chapter we're going to learn about the energy involved in bonding. In Honors Chem you've learned a lot about how to draw your molecules, how to do Lewis structures, the 3D shapes, but we don't talk a lot about the energy that's involved in the bonding process, and that's what we're going to learn about today. You should remember from Honors Chem and earlier this year that we learned about things like electronegativity, atomic radius, the charge that ions can make, and those things are going to end up being really important in this chapter because when we're talking about the energy involved in bonding, once again, just like before, it's going to come down to attractions and repulsions. And so we need to make sure that we're really strong on those periodic trends and that we can use those to justify and talk about some of our answers for the energy of bonding here. If you remember, an ionic bond is when the electrons are completely transferred from one atom to the other. In the process, you end up making ions. The bond itself is not the transfer. It's not the act of transferring. It's the result of the electrostatic attraction between the ions that were formed during the transfer. So the electrons are transferred. You now have a positive charge and a negative charge, a cation and an anion, and those two ions are electrostatically attracted, and that attraction is what we call the ionic bond. So I just want to make sure everybody kind of understands that the bond is not the act of transferring, it's the result of transferring. You can use a chart of electronegativity values. Sometimes this is nice because it gives you a nice clear-cut answer. The problem is that not everybody agrees on where the cutoffs are. Most things I've seen, most things we'll use in this class will be a difference of 1.7 being the cutoff. So anything bigger than that would be an ionic bond. When ionic bonds form, energy is released. Remember, things want to be at a lower energy state. They want to be more stable. They want a more favorable outcome. And so by those bonds forming, they end up more stable. They end up at a lower energy position. They release that extra energy, and that's why it's exothermic. We see heat released. One of the things that's important is that you remember some of the general characteristics of ionic compounds versus covalent compounds. And one of the things that you typically end up doing in Honors Chem is thinking about ionic bonds as, oh, it's a metal and a nonmetal, and that makes it ionic. Well, you have to be a little careful of that. It's better to say it's a cation and an anion because you could have polyatomic ions and not have any metals present. Another thing that's important is that you understand that it is not just the electronegativity difference that decides if something is ionic. Their characteristics come into play as well. You have to have a large electronegativity difference, and the compound, when it's in a molten state, meaning you've heated that solid up and now it's hot enough to be a liquid, when you heat it up to a liquid, when it's molten, it needs to be able to conduct electricity. It needs to be able to have the electricity flow through the material. So just be a little bit careful that you are not relying only on your little subtraction value. You have to also think about the characteristics if any information related to that is provided to you. The big deal in this chapter, and most of AP Chem, they love this, is Coulomb's law. So this is mathematically describing the attractions between the charged particles. We see an equation that you may see represented in slightly different ways, not a big deal. We way oversimplify it here. The simple version that you're going to see looks like this, where the force is proportional to these Q values divided by R squared. Q is a measure of the charge on the particles, like it's a +1 ion or a +2. So you're looking at that charge, and we typically take the absolute value of that. R is that distance between the particles. You may sometimes see it with a K value, with that constant. That's a little bit better, right? Because it's going to take into account more specifically the exact substances. It's a correction value, right? You may also see it look really crazy like this. This big crazy thing is what K is representing. This is how they calculate that K value. That's not the same as the rate constant, okay? So it's really important that you understand that we're using a simplified version, okay? We're really just talking about whether things are proportional, right? We're not even necessarily calculating it. They want you to describe that the attraction would go up as the size of your charges goes up, and your attraction would go up when you have a small distance. And if you think about magnets, that makes sense, right? If you have strong magnets and they're close together, you'll feel a really strong pull. If you have weak magnets or the magnets are very far apart, you're not going to feel a very strong pull. So a similar idea here. Make sure that you remember that like charges repel, positive and positive repel, negative and negative repel. If you want them to be together, if you want them to be close to each other, it would require energy to push them together. That means that the energy there would be positive. It's not good, right? And they would decrease, they would be more stable, right, as they get further apart. Compare that to our opposite charges. When you have two ions coming together, right, they're attracted to each other. They are better off together than they were apart. They have that negative potential energy, more stable. And as they get closer and closer, that energy becomes more negative. So, when we have a large charge, we end up with an increase in our attraction. The electrons are going to be more attracted to a +2 than a +1. So if I want to look and see what would the strongest ionic bond be, it would be something with a very large charge difference. Maybe you have a +2 versus a +1. Works for negative as well, right? -3 versus a -2. The larger the charge, the stronger the bond. And the smaller the radius, the larger the stronger the bond. So large charge and small radius gets you a nice strong bond. If you don't remember what charge your ions make, you're going to have a hard time with this. If you don't remember your ionic radius patterns from the periodic table chapter, you're going to have a hard time with this. We are seeing those periodic trends come back to us, all those fundamentals from Honors Chem. One of the characteristics of ionic compounds is that they like to make what we call crystal lattice. So you end up with a very organized structure of your positive and negative ions stacking together in a three-dimensional space. Once upon a time, you used to have to learn all sorts of fancy names for the three-dimensional arrangements of the ions. We don't have to do that anymore, thankfully. But depending on what type of ions they are and what size they are, they can arrange in different patterns. But the three-dimensional structure they take, we call a lattice, a crystal lattice. If you want to take a lattice apart, we use what's called the lattice dissociation energy. And the values that you would see in a chart or in a question are typically given to you if you are taking apart 1 mole of the substance. I clearly was not going to try to draw 1 mole of circles here, so just pretend. It takes energy to pull it apart, right? Because those positive and negative ions are more stable together. They're at a lower energy, so takes energy to separate them. Most of the time, we are talking about formation energy, okay? We are interested in the energy involved in forming our crystal lattice. So going the opposite direction, right? And pretend once again that we have a mole of everything. So what I'm going to do is I'm going to walk you through the various steps, and we're going to talk about what steps have to be taken. What do those steps look like? Does it take energy, or is energy released for each step? It's very important that you remember the steps of your lattice formation. So let's say we want to form a crystal lattice of lithium fluoride. The very first thing we have to understand is that our lithium is going to start as a solid. And solids don't do much for us. We need to get it into a gas form so that it's more able to form our structure. So when we take a solid and we turn it into a gas, if you remember, that's called sublimation. So I have these close packed solid structure, and I'm going to turn it into a gas. Now, fluorine, you have to remember, is a diatomic gas in its natural state, right? At room temp is going to be fluoride, F2 gas. Well, we don't want two of them up here, do we? Diatomic fluorine is not going to do much for us. It's not going to be reactive, do much. We need to break it apart to get just one fluorine atom in a gas state. So that's the bond dissociation energy. It's going to take energy to break this bond between these atoms. Now we have some neutral atoms. But lithium fluoride is not made from neutral atoms, is it? These are ions. I need a lithium cation and I need a fluoride ion, anion. So it's going to take some energy to ionize that lithium. Remember, it's 1 mole of it. We're trying to ionize an entire mole of lithium here. We need to remove an electron to turn it into the cation that we're trying to make. Now, to get fluorine to turn into fluoride, it needs to gain an electron. That's not ionization energy. Okay, remember that is the electron affinity, gaining the electron. Now I have my purple cation and my green anion. I have a lithium ion and a fluoride ion, and now they can be attracted to each other to form that lattice. So let's think about whether it takes energy for each step or if energy is released. It is going to take some energy to turn a solid into a gas. It's going to take some energy to break the bond there. It takes some energy to remove an electron. Even though lithium likes making a +1 charge, even though it's fine being an ion, you still have to put a little bit of energy in to remove it, right? Now, a fluorine atom is more stable and better off being a fluoride anion. That is going to be a release of energy. That's what the electron affinity measures. Remember, it's measuring how much energy is released, how much more stable is it afterwards. So that is going to be a release of energy. And then our positive and negative ions being attracted to each other to form our lattice is also a release of energy. If you add all these steps together, you would end up figuring out how much energy was involved to form your final structure. You will often see pictures like this. A lot of people kind of freak out when they see these graphs. They see all these arrows and all these numbers and all these equations, and they're like, I can't even think about this. Well, you have to, okay? You don't have the luxury of getting overwhelmed. You have to think about each step individually. So literally just look at each step. What's happening here in step 1? I'm going from a solid to a gas. Well, that's sublimation. And look, it took a little bit of energy. It was endothermic. Now here, we're trying to break a bond. Well, that's that bond dissociation energy. Takes some energy. Here, I'm trying to ionize my sodium into a cation. I'm taking away an electron. That's going to be ionization energy. Over here, step 4, I'm trying to turn this into an anion. I'm trying to go from a chlorine atom into a chloride ion. That's the electron affinity. Look how much happier it is now, right? It's lost all this energy. More stable, happier. Please, on your FRQs, do not write about atoms being happy, okay? It's good to personify them to understand it, but you got to move past that in your answers. Now down here, look what's happening. I have these two ions coming together to make my solid. That's the lattice energy. And if I add up all these values, I find out the total overall net energy. And that's the enthalpy of formation for that crystal lattice, isn't it? And look, for this, it's more stable afterwards than when it started. I really like these graphs that show the direction up and down of the arrows. Sometimes you'll see graphs like this. I think these are a little bit harder because I think they're mainly just trying to save space here, and they don't really show a total net overall up and down because these side-to-side arrows I think are a little bit tough. But when you get to one like this, once again, just look at each individual step here. This arrow going down here is lithium, solid to gas. That's my sublimation, and that takes energy. Going from a neutral lithium atom, losing an electron, that's my ionization. Here, this arrow is trying to show you taking your fluorine gas, diatomic gas, and breaking that bond. That's that bond dissociation energy. Over here, this arrow is trying to show you gaining your electron. That's the electron affinity. And then over here, they're taking these ions and putting them together to make your lattice. That's your lattice energy. Sometimes they'll ask you to identify, like, what's step 4? What is step 2? Which one is the lattice energy step? Always look, they'll give you the little equations. And if it's, the nice kind that I like, great. If it's kind of the space-saving, more old-fashioned way, just baby step your way through it. It's always the same steps. They may represent them in different directions or write them in different ways, but it's always the same types of steps. Sometimes you're going to see people talking about lattice energy in a way that looks very similar to Coulomb's law. They have a proportionality constant, that correction value that's based on the specific substance you're talking about. They have the charges. You may sometimes see capital Q's instead of lowercase. And the thing here is they'll use R instead of R squared. It really doesn't matter. We're not typically doing mathematical equations. We're really looking at these in terms of, proportionality. Like, oh, look, my attraction goes up when my charges go up. Look, my attraction goes down when my radius gets bigger. those types of things. Sometimes they will ask you questions about how strong is the bond. And what they're really asking you to look at is the enthalpy of dissociation in terms of the overall formation. It's the same concept though, isn't it? If it's a lot of energy is released when something forms, that means it's going to take a lot of energy to break it apart, right? So which means it's very strong. The sign will be different, right? It'll be a positive instead of a negative, but it's the same constant or the same concept. If you look here, right, if it's negative 617 is, when you form it, well, it's going to be positive 617 when you try to break it apart. They're trying to see if you understand that these are opposite processes and you don't really need an opposite graph. You're just going backwards. You may have to do calculations of lattice energy. You're not expected to know the values. They will give you the values in a big chart, but they will often not give you the values in order, which is tough. So I always suggest that you think of your order and then go find your number. Don't look at the big chart and get overwhelmed. So we know that our sodium needs to sublimate. It needs to go from a solid to a gas. So I come over to my chart and I find the value for sublimation. I know that my sodium has to turn into a cation, which is ionization, so I find that on my chart. I know that my chlorine starts as a diatomic element, and I need to get it into just a single chlorine. One of the things you need to be careful of is that you take into account your coefficients here, right? Because we're trying to make 1 mole of sodium chloride, I need a 1/2 coefficient here. But this value in my chart is for 1 mole. So I need to take 1/2 of that value. Then my chlorine atom needs to gain an electron to turn into a chloride anion. That's the electron affinity. Now I have my cation and my anion, and they can come together and be electrostatically attracted and form that nice crystal lattice. That's where I come up here and I look for the lattice energy. Does this remind you of anything? Look, I have a sodium on each side. I have a sodium cation on each side. I have an electron on each side. I got a chloride on each side. Chlorine atom on each side. Chloride on each side. I'm left with my overall reaction. I add up all my values. That should remind you of your Hess law. It's the same thing, isn't it? There is a reason we start the year teaching Hess's law. Because if you have a good understanding of Hess's law and that a reaction is the sum of all the baby steps, learning things like lattice energy becomes much easier. Common mistakes here, people completely forget that they have to do all the baby steps and they just look for lattice energy and give that answer. Nope, lattice energy is one step. It is not the total energy that's involved, that's just the energy of that last step. And then the other one is forgetting things like your coefficients and forgetting that we're after the value for 1 mole of it. And as always, double check your units, make sure that they actually want kilojoules, make sure your chart is in the right units, things like that. Switching gears a bunch, now let's take just a brief reminder about covalent bonds. Remember that we have two types here. We have polar covalent and non-polar covalent. Polar covalent are where those electrons are unequally shared. You can use those electronegativity differences to see that. Once again, remember the cutoff values can be very different based on which textbook you're looking at. Non-polar, where they're sharing very equally. Now, in honors chem, because we don't typically cover the electronegativity difference subtraction, because the charts are also different, we typically will tell you that non-polar covalent bonds have to be the same atom, like 2 fluorines or 2 hydrogens. Technically, it could be 2 different atoms if they have a very small electronegativity difference. So it's not a perfect nonpolar. It's not exactly 100% nonpolar, but it's such a minimal unequal distribution that it doesn't affect the properties. And so kind of like how we talked about ionic bonds are defined not just by their electronegativity difference, but also their properties, we do the same thing here for nonpolar covalent. It's not just their electronegativity difference that you look at. It doesn't have to be exactly 0. We look at the properties. If it's not a big enough difference to affect the properties in a significant way, we say it's nonpolar. So 0.3, yeah, good enough, right? Like 0.2, good enough. You will always be provided a chart to compare to with the cutoff values provided. Otherwise, just talk about it conceptually. Remember, once again, this is about attractions and repulsions, right? Those electron-electron repulsive forces, proton-proton, versus the electrons and the protons being attracted to each other. We will often be thinking about the bond length in our covalent bonds and the energy involved in different types of covalent bonds. You've seen this picture before where we have our separate atoms. As they get closer and closer, they start to get to a more favorable energy position. They have a lower energy. Down at the bottom, the trough, that's where we say they have officially bonded. And that is the bond length. If I come down here and read on my X-ray, I can see what my distance between atoms would be. If you keep smashing those atoms closer and closer, those repulsive forces between the protons start to kick in and the energy goes sky high, doesn't it? So we say they're bonded at their lowest, most stable energy position. And the analogy I like is Goldilocks, right? Too far is bad, too close is bad. You want it just right down at that trough. You'll see a variety of graphs like this. You should be able to read your energy and your bond length off of the axes. You should be able to explain why the energy goes higher if they get too close. One thing that we see with the bond length is that as you go from a single to a double to a triple bond, the bond length changes. Now let's compare apples to apples. Let's look at just a carbon-carbon bond here in green. Look, single bond to double to triple. Look what happened to the bond length. It went down. They get closer together. And look what happens to the energy. It goes up. The bond is stronger, closer together. Look at here, carbon-oxygen bonds. We see the same thing. Single to double gets shorter and it gets stronger. It would take more energy to break this bond, the double bond, than it would to break the single bond. Look at this carbon-nitrogen bond. We see the exact same pattern. So what we say is that the bonds become shorter and stronger as the multiplicity increases. That is just a fancy vocab word that helps us describe going from single to double to triple. Triple bond, shorter, stronger. It gets a little tougher if you're going to start comparing apples and oranges. If you're going to start talking about the carbon-carbon bond versus a carbon-oxygen bond, you're going to have to think a little bit more about electronegativities. You're going to have to think about the radius. You're going to have to think about all that stuff. We practiced a little bit calculating bond energy in an earlier chapter. I like to introduce it early and bring it back when we get to this point. So remember that the overall energy is going to be the energy required to break those bonds minus the energy released when those bonds are formed. Once again, be careful that you remember these are per mole. If they give you grams, you're going to have to convert to moles and then do the problem using that conversion in there. You have to remember that it takes energy to break a bond. You have to physically separate them. You have to pull them apart, right? It takes energy to break a bond. Otherwise, they just spontaneously wouldn't be together anyways, right? You have to remember this. It's one of those thou shalt not forgets, right? And when you make a new bond, you are releasing energy because it is going to be more stable. Otherwise, it wouldn't form, right? I have noticed people here struggle with getting the signs correct. They get their subtractions backwards. I much prefer just the little reminder takes to break, freeze to form. So when I do a problem like this one, how much energy does it take to break 2 waters into H2 and O2? Well, I would be breaking 4 OH bonds. Breaking is positive. I'm going to be making 2 hydrogen bonds and 1 double bonded oxygen. Making is negative. So when I write out my equation, I'm going to have 4 positive values. I'm going to have 2 negatives here, and I'm going to have 1 negative here. 4 positives, because that's what it took to break. I have 2 negatives of these because it's forming. And I have 1 negative of this because it's forming. When I think of it that way, I don't get my subtractions out of order. Now, one thing that we have to start doing now, at this point in the year, now that you've officially seen Coulomb's law, now that you're going to practice it when you talk about bonding, when you're going to talk about the charges and the radius and all of that, is you have to start using that to talk about your periodic trends. We've tried teaching Coulomb's law officially in the periodic trend chapter, and to be honest, I've never felt that it went very well. I think it's better to kind of teach the periodic trends in a bit more simple way, a bit more conceptual, then get to bonding energy, introduce Coulomb's law, and then say, guess what? Now you can use that to talk about your periodic trends. I love this little cartoon with Winnie the Pooh, right? The best answers are going to now combine these 2 ideas. We aren't just going to describe the trend. We're not just going to talk about the nuclear charge and the shielding. Now we're going to also reference Coulomb's law and really use that to talk about that attraction. All right, everybody, that was it. I hope that was helpful. Bye.